This is Chaya Chandrakar from Sri Venkateswara College of Engineering. Today we will study about the topic series expansion in computer programming. We are going to learn about what is series expansion and what is computer programming, and the types of series expansion and implementation and programming, and then challenges in series expansion and real-world examples. First, let us know what is series expansion in computer programming. A series expansion is a way to represent a function as a sum of powers of one or more variables. Series expansion is a mathematical technique used in computer programming to calculate functions that can't be expressed by basic operators. Series expansions can be used to approximate functions and find equivalence between them. So now let us know what are the types of series expansion. First is Taylor series, a power series based on a function's derivative at a single count or a single point. Maclaurin series, a special case of Taylor series centered at zero. And then Lorentz series, an intention of the Taylor series allowing negative exponent values. And Dirichlet series used in number theory. Stirling series used as approximation for factorials. Zernike polynomials used to optics to calculate the aberrations of optical systems. Newton series legendary polynomials used in physics to describe an arbitrary electrical field as a superposition of a dipole field, a quadrupole field, and a octadipole field. Fourier series describes a periodical function as a series of sine and cosine functions. Now let us know what is Taylor series expansion. Taylor series is a polynomial or a function of an infinite sum of terms. Each successive term will have a larger exponent or higher degree than the preceding term. The above Taylor series expansion is given for the real values function f of x and where f dash of a and f double dash of a and f double triple dash of a, etc. denotes the derivative of a function at point A. If the value of a point A is 0, then the Taylor series is also called as Maclaurin series. So, the formula for Taylor series is f of x is equals to f of a plus f dash of a into x minus a plus f double dash of a divided by 2 factorial into x minus a to the power 2 plus f to the power q into a divided by 3 factorial into x minus a to the power q, as so on. F to the power n into a divided by n factorial into x minus a to the power n. So here let us know what is Maclaurin series expansion. Maclaurin series is a special case of Taylor series when x is equals to 0. It is a function that has an expansion series that gives the sum of derivatives of that function. So like Maclaurin series formula is y of x is equals to y of 0 plus x to the x is divided by 1 factorial into y dash into 0 plus x to the power 2 divided by 2 factorial into y double dash into 0 plus x to the power 4 divided by 4 factorial into y to the power 3 into 0, which will so on go till nth term. So now let us know how all of the series expansion is implemented in programming. So first let us know how Taylor series is implemented using programming. Let us take an example of x to the power e to the power x up to 10th term degree. So here, to know the expansion, we'll be using Python. So using Python, let us know how the implementation of programming is done for e to the power x. So first, this Python code calculates an approximation of exponential function e to the power x, which will be done using the Taylor series expansion. So first, let us consider the import math. So import math module will be used for math factorial function, which computes the factorial of a number. And then here you can see we have defined a function. So the function is Taylor expansion in the range of e to n. And then next we have result. So the result is equals to 0. So here we'll know that this function takes two inputs. So one will be x, as we can see x. So the value of x for which is calculated, and n will be the terms, the number of terms in the Taylor series to include in the approximation, and the result will be initiate to 0, and then which will show store the cumulative number of series. And then here will be computing the Taylor series. We'll use a loop iterates through the first term and the first n terms of Taylor series, and the term is added to the cumulative result. Later we have the return result. So the return result after the loop cumulative sum is stored, and the result is stored, and then the result will be returned. And then we have a function call over here, as you can see, print Taylor expansion 1 to 10. So this is the function call. So here we'll print the Taylor expansion from 1 to 10. That means the function is called with the x is equals to 0 and n is equals to 1. Means the first 10 terms of Taylor series for x to the power e to the power 1 are used to approximate the value of e. So when we execute the program, we'll get the approximate value of e. So as we can see the output of the result, so the output will be 2.7182815255 and so on. It will be the approximation using 10 terms of the Taylor series, so which is approximately 2.71828, so which is very close to the actual value of e. So using the using the Python code, this is how we execute the Taylor series. For example, we took e to the power x. So using this Python code, we can solve the series expansion of Taylor series expansion. So here when we execute the program we are using certain module, and we are defining a function, and then we'll be returning the result, and then we are using a loop for the execution in the range of 1 to 10, and then we'll get the return result, and we are printing the function, like we are using a function call for the execution of the program, and later when we run the program we'll get the value of e, which is 2.182182815 so on. So this is if we consider 2.71828, so this is the approximate or close value of e. So using this we can do, or we can learn Taylor series expansion in programming. So let us know the next example which we took, Maclaurin series. We'll consider Maclaurin series and know the next programming or a question which can be solved using Python. So in this slide, we will take an example of Maclaurin series. We'll use a question as an example and let us know how to solve it using a Python program. So when we use the question, we have taken here a sin x plus cos x. So let us know how to use a Python program and solve the series. So in this question, first we have to import certain libraries, like import nymph as NP, and then from matplotlib import pyplot as PLT, and from SymPy import. So here importing libraries like import nymph as NP and import pyplot and SymPy. So here we can know what is NumPy, and so NumPy is used for numerical calculations and creating arrays, and matplotlib import .pyplot is used for plotting the graphs, and SymPy is used for symbolic computations like differentiation and symbolic math. And then next we can see we have done the symbolic representation. The symbolic representation for a function x, and then here you can see we have symbol xy is equals to, we have defined the symbol x, and then we have taken the function which is y is equals to sin x plus cos x, and here again a symbolic variable x is defined using the symbol, and the function is defined symbolically. So using this we have defined the function symbolically, and then we have set the initial condition of x using which is equals to float 0 is the point at which the Maclaurin series is calculated, and then we have differentiated the terms. Here we have differentiated as dy is equals to differentiate by x, and then we have differentiated again, which will be differentiation of xy2, and then the first and second term, like as it goes on, the first, second and third derivatives with respect to are calculated using differentiation. And then converting symbolic expressions to function, we have used lambdify, I'm sorry. So this lambdify function will convert the symbolic expressions into the Python function for numerical evaluation or calculation. And then you can see we have used the Maclaurin series formula for the calculations. So this constructs like Euler expansion up to third degree. We have taken up to the third degree because we are knowing the answer till the third term or the third degree. And then we have used a print function. So print functions we have used simplify y is equals to, we have first simplified and then converted into radians like the angle, and the Maclaurin series is simplified and printed over here, and then the value of the Maclaurin series is converted, and then here we have used plot, which will be done for the plotting of graph, and then here the graph is plotted in the range of -10 to 10, and then we have used the grid for the clear graph presentation. And then let us know about the graph, output and the graph. So here as we can see, the graph is presented in two different colors, which we are again defined in the function itself, red and green. So here in the approximation in red, and then the original function is in green. So the Maclaurin series approximation was in red and the original one is in green. The plot limits are set and the grid is added for the clear ends of the graph, and then the graph represents comparison between the original function, which is a green curve as you can see, and the Maclaurin series approximation is in the red curve. So let us know what this graph defines, and then the green curve, which is the original function as we took sin x plus cos x, the green curve represents which is smooth and the periodic function. There is a periodic change in the function, and the function oscillates between with the period of time. And then the red curve represents the third degree, which we took the expansion till the third degree, and then this expansion So in this expansion, as we can see, that the Maclaurin series expansion and the polynomial expression, that matches the value on the first three derivatives of the original function. And then, so here if we compare the graph, like for more clear understanding, like the red curve closely follows the green curve. This is because the Maclaurin series is designed to approximate the function accurately near the expansion point. Like the curve, the red curve closely follows that green curve, where the Maclaurin series is approximate the function accurating the expansion point. So here in the graph, if we observe, the approximate point is 0. So in the graph we can understand the approximate point here will be 0. So where the two curves are meeting or coinciding. So if we the output we get is 1.082. So let's go for the next slide. So now let us know the challenges in series expansion. So calculating factorial and powers repeatedly can become a computational expensive and especially for large. And then here error decreases rapidly, and then logarithmic scale and trade-off. So here with respect to error, the error drops significantly as the number of terms increase, indicating better accuracy. For the error is very close to 0. And then in logarithmic scale, the y-axis uses the logarithmic scale to highlight how quickly the error decreases. And trade-off, while increasing terms improve accuracy, there is a computation cost to adding more terms. In practice, stopping at provides sufficient accuracy for most applications. So this will be the major challenges faced in series expansion. So the programming might remove all of these complications. It might be very easy for executing or getting the proper accurate answer. So you need theoretically practice all of this expansions. There will be so many challenges. So implementing the language while solving can be easy and makes the work on time. So now let us know a few real-world uses and applications of the series expansion. The practical application of series expansion in various fields of computer science, engineering, and real-world problem solving. It showcases how Taylor, Maclaurin, and Fourier series are essential tools in computational system. It is used in machine learning and data science, computer graphics and animation, and then numerical methods and scientific calculation and engineering application, and even used in astronomy and space exploration. Thank you for watching the video.